Like, subscribe, and hype the video. Also, leave a comment on any topics you want to hear about in the future. Okay, let's dive in. Before there was space, there was no space. Before there was time, there was no time. Before there was anything at all, no matter, no energy, no darkness, no emptiness, because even emptiness requires space to exist in, there was nothing. And then, approximately 13.8 billion years ago, something happened that we call the Big Bang. Not an explosion in space, but an explosion of space itself, from a state of almost incomprehensible density and temperature, expanding outward in every direction simultaneously, carrying matter and energy and the very fabric of space-time with it. This is the story of what actually happened. Not the cartoon version, not the simplified version, but the real sequence of events in the first seconds, minutes, and years of the universe's existence, and the evidence that tells us this story is true. We're closing out this entire series with the biggest question of all: where did everything come from? And in our next episode, we're getting into what came before the Big Bang and the conspiracy theories that claim the whole thing never happened at all. Stick around for that one. The most important thing to understand about the Big Bang is what it wasn't. It wasn't an explosion happening inside existing empty space, with matter and energy flying outward from a central point into a surrounding void. That image, intuitive as it feels, is wrong in a fundamental way. The Big Bang was an expansion of space itself. There was no surrounding void to expand into. There was no outside the universe, because space didn't exist outside the initial state. The expansion happened everywhere simultaneously. Every point in the universe was the center of the Big Bang, because every point in the universe was the same point at the moment the expansion began. This distinction matters because it changes what questions are even meaningful to ask. What was the Big Bang expanding into? Assumes there was pre-existing space surrounding it, but there wasn't. Where did it happen? Assumes a specific location within pre-existing space, but the expansion of space is not a location within space. It's the creation of space. These questions feel natural because our intuitions are built around existing inside a large pre-existing space. But the Big Bang defies those intuitions at a fundamental level because it represents the origin of the space those intuitions are built around. Like, subscribe, and hype the video, because the first fraction of a second of this expansion contained more dramatic physics than the next 13 billion years combined. The physics of the Big Bang's first second is among the most precisely calculated and experimentally tested knowledge in all of science, despite describing events that happened 13.8 billion years ago at conditions that can never be directly recreated. At the earliest moment physicists can meaningfully describe, a time called the Planck time, roughly 10 to the negative 43 seconds after the Big Bang, the temperature of the universe was approximately 10 to the power of 32 degrees, and all four fundamental forces were likely unified into a single superforce. Our physics breaks down completely before this point, and what happened before the Planck time is genuinely unknown. After the Planck time, but still within the first tiny fraction of a second, the universe went through the rapid expansion of inflation we discussed in our multiverse episode, growing by an enormous factor in an almost instantaneous burst that smoothed out its initial conditions and set the stage for everything that followed. As the universe expanded and cooled, the fundamental forces began separating from each other, gravity first, then the strong nuclear force, then the electroweak force, a process called symmetry, breaking that established the distinct physical forces we observe today. By about 1 microsecond after the Big Bang, the universe had cooled enough for quarks, the fundamental particles that make up protons and neutrons, to begin binding together into the first hadrons. Protons and neutrons began forming, along with their antimatter counterparts, in nearly equal numbers. The fact that matter and antimatter were created in almost but not quite equal amounts, with matter winning by roughly 1 part in a billion, is one of the deepest unsolved puzzles in physics. That tiny asymmetry is the reason the entire observable universe, every galaxy, every star, every atom in your body, exists rather than having annihilated in a burst of pure radiation. About 1 second after the Big Bang, the universe had cooled enough that the balance between protons and neutrons became fixed. The ratio locked in at roughly 7 protons for every 1 neutron. This ratio mattered enormously for everything that followed. Between about 1 second and 3 minutes after the Big Bang, the universe went through a process called Big Bang nucleosynthesis, the formation of the first atomic nuclei. Protons and neutrons began fusing together under the extreme temperatures and densities still present at this early stage. Deuterium formed first, a nucleus containing 1 proton and 1 neutron, followed by helium-3, helium-4, and tiny amounts of lithium. By the end of Big Bang nucleosynthesis, roughly 3 minutes after the Big Bang, the universe's elemental composition was essentially set, approximately 75% hydrogen and 25% helium by mass, with trace amounts of lithium and other light elements. This specific ratio is one of the most important predictions of the Big Bang model, and it's been confirmed precisely by measurements of the oldest, least chemically processed stars we can observe. Stars that formed early in the universe's history and whose composition still reflects the primordial abundances from those first 3 minutes. Like, subscribe and hype the video, because for the next 380,000 years after those first 3 minutes, almost nothing happened at all, and then the universe suddenly became transparent. For the first 380,000 years of the universe's existence, the cosmos was completely opaque. The universe was filled with a plasma of charged particles, protons and electrons, and photons of light couldn't travel more than a short distance before being scattered by one of these charged particles. The universe glowed brightly but was essentially foggy, with no light able to travel freely in any direction. Then, 380,000 years after the Big Bang, the universe had expanded and cooled enough that electrons and protons could combine into neutral hydrogen atoms for the first time, a process called recombination. The moment this happened, the universe became transparent almost instantly. Photons that had been constantly scattering off charged particles suddenly had nothing to scatter off. They could travel freely in straight lines across the cosmos for the first time. Those photons are still traveling today. They fill the entire universe as a faint background of microwave radiation, the cosmic microwave background, or CMB, detectable in every direction we point our instruments. The CMB is a direct snapshot of the universe as it appeared 380,000 years after the Big Bang, and it's one of the most powerful pieces of evidence we have for the Big Bang model. Its temperature is extraordinarily uniform across the entire sky, varying by only about 1 part in 100,000, but those tiny variations in temperature correspond to tiny variations in the density of matter at that early time, which seeded the formation of all the large-scale structure we see in the universe today, all the galaxies, galaxy clusters, and cosmic filaments that eventually formed from those barely perceptible ripples in the early universe's density. The Big Bang isn't a belief or a philosophical position. It's the most extensively confirmed scientific model for the origin and evolution of the universe, supported by multiple independent lines of evidence from completely different measurement techniques. The cosmic microwave background, the primordial abundance of light elements matching nucleosynthesis predictions, the observed expansion of the universe in all directions with more distant galaxies moving away faster, and the observation that galaxies in the early universe looked different from galaxies today. All of these independent measurements, using completely different instruments and methodologies, converge on the same picture of a universe that began in an extremely hot, dense state, roughly 13.8 billion years ago, and has been expanding and cooling ever since. The predictive success of the Big Bang model is extraordinary. The temperature of the cosmic microwave background was predicted theoretically before it was ever measured, and when it was measured, it matched the prediction with remarkable precision. The ratio of helium to hydrogen was calculated from first principles before it was confirmed by stellar observations. The detailed pattern of temperature fluctuations in the CMB was predicted by models of early universe physics years before instruments sensitive enough to measure them existed. In each case, the prediction came first and the confirmation followed, the hallmark of a genuinely powerful scientific theory. So here's what we actually know about the Big Bang. The expansion of space-time from an extremely hot, dense initial state, the formation of the first particles within the first second, the locking in of the matter-antimatter asymmetry that allowed the universe to exist at all, the nucleosynthesis of hydrogen and helium in the first 3 minutes, the transparency event at 380,000 years that we can still observe today as the cosmic microwave background, all of it confirmed by multiple, independent, precise measurements that have held up to over 60 years of increasingly rigorous testing. But there's one question the Big Bang model itself cannot answer, and it's the most natural question anyone asks when they first hear about it. What came before? What caused the Big Bang? What existed, if anything, before the expansion began? In our next episode, we're going there, into the territory before the Big Bang, what the most serious scientific proposals actually say about it, and the conspiracy theories that claim the entire story is wrong. This is the final episode of the series. Make it count. Stick around. Like, subscribe and hype the video so you don't miss the series finale. And let me know in the comments what you think came before the Big Bang. I'll see you in the next one.